Joaquim Oliveira from the European Space Agency is going to be talking about moving big data, big science workloads from Greenplum to alternatives. Enjoy.
Thank you. Again, apologies for the delay, but it seemed that this conference doesn't like my laptop, and it's really hard to extract information from my laptop. But hopefully, I had a really cool Portuguese guy here who lent me the laptop, so we can continue with this. We'll have to speed up a bit because we are 17 minutes late. So, my name is Joaquim Oliveira. I work for the European Space Agency. I'm a software engineer that some years ago decided to go further into databases. Basically, we had an issue. We are a big team. We only had one DBA, and someone asking, does anyone want to help Pilar in the DBA tasks? And everyone was whistling to the side, and I said, well, why not? I like science, so let's try this. So I'm just going to explain a bit what was our journey on choosing technologies for storing big catalogs in databases. Okay. So does anyone know what is ESA? Wow. And NASA? JAXA? CSA? Canada? Okay, so in Europe, we have the European Space Agency. It belongs to the member states. It's founded by some countries that founded ESA, and now it's funded by a lot of more member states. Probably here you belong at least from one of these countries, mostly. And what is ESTC? The ESTC is the European Space Astronomy Center, Science Data Center. Yes, center 2 times. That's it. We have archives. You can follow this QR. We have a lot of archives, and we store all of the science missions data. So we are not only software and databases. We are also a team of I don't know, maybe 60, which around 40 are engineers. I'm somewhere in this picture. We work on a site that used to be a ground tracking station. So the only construction that you see beside us is this old castle. And what do we do? Missions get launched into space. By the way, do you know the name of the people that go inside these rockets to go to space? Astronauts? Maybe? And in Russia? Cosmonaut. And in China? Well done. Who said it? Okay. I could go on. There are a few more, but I mean, space is a funny thing. So we launch rockets into space. We have spacecraft flying. Does anyone know which spacecraft is this one? Sorry? Gaia. Well done, Gaia. So Gaia is a mission that it has as main objective to create the biggest 3D map of stars in the Milky Way. Then, when this spacecraft starts taking pictures, this works like these big cameras that you can see, but a lot more complex, of course. We downlink data to ground stations. From the ground stations around the world, this goes to Germany, to the European Science Operations Center. We get information in our site, which is, as I said, in Madrid, the European Space Astronomy Center. And then, after we process all the data, it's stored in our beautiful data center that you can see here. So basically, in a nutshell, this is what we do at the ESTC. We store all of the of the science data from the science missions. This is more or less an estimation on the archive's size at this point. So we have mostly been growing with almost no data to we are at a point of having 1 petabyte of data. Next year will be around 4 petabytes of data. This is data. This does not represent databases, but database-wise, we are talking about in next year probably 400 terabytes in databases. And as you can see, the numbers are going to grow a lot in the coming years because missions get better instruments generate more data, all the scientists want to see all the data, so we have to store everything. So that's our mission. And we have to store this data forever because member states and you, with your taxes, if you're from one of these member states, are paying to have this data available forever. That's going to be our legacy, to have all this science data in our archives. Regarding technologies, we mostly use Postgres from 13 to 17, hopefully 18 in the near future. We also use Oracle and also other small usages of Elastic, MySQL, Apache, Spark, but mostly we work with Postgres. Okay, we have around 100 databases in Postgres, and we have like 6 Oracle databases, which is basically one mission only, but with 6 databases. Then we start having issues because we reached a point that we cannot scale up anymore. We had really big databases, and we reached a point that we would need to have really powerful hardware, really expensive hardware, to be able to run a query. So our queries, we are not going to receive 2,000 queries per second. No, we are going to receive really big queries, but with a different distribution in time, because there are not a lot of scientists that want to access that information. So instead of scaling up, we started checking the options to scale out, to have different instances of smaller database engines. As I was saying, we had this big single instance database. I mean, a lot of cores, a lot of RAM, etc. And we start planning out for having, now there's already saying here, Greenplum, I'm already getting ahead of myself, but we started preparing a scale-out solution based on Greenplum, using workers, which would have less resources, but they would divide the work among them. But as you saw on the plot, we started this journey with this tsunami coming to get us. So we have all this data that you saw before in the plot. That data is coming. We cannot do anything. That data is coming, so spacecraft will be launched, spacecraft will operate, and data will start to arrive to our file systems. And we need to ingest that data, and we need to put that data in order for the scientists to do their science, because that's their work, right? So we cannot delay also. We really need to do this. So the plan for the scale-out tests, this was made around, well, before 2018. Well, we had this big plan to, well, we need big data sets. Data sets are hard in space because you can generate synthetic data, but the universe doesn't follow a distribution. It's not uniform. It's harder to generate data that you can simulate for. So basically, we started using Gaia as one of the sources of data, because it started creating this big 3D map of the stars in the Milky Way. So we wanted to start comparing between single instances and scale-out solutions regarding ingestion times, because this is important. We have this data coming, and we need to put it available for the scientists as soon as possible. Also, retrieving time. Scientists want to download everything. If your archive has 1 terabyte, they want 1 terabyte. If it has 1 petabyte, they want 1 petabyte, even though they don't know where to put it, but okay. So prior to 2018, we started checking a lot of solutions. Does anyone know PostgreSQL? Yeah, good. So you're all this, sorry. Citus, I think you all know Citus. Greenplum, does anyone know what Greenplum? Wow, that's why you came here. I thought you were coming here to ask me questions about that big spaceship. I don't know. Nah, it's not a spaceship for sure. For sure it's an asteroid or something like that. Extra solar system comet or something. I don't know. Don't ask me because I don't know that information. And even if I know, I could not tell you, okay? So around 2018, we decided to go with Greenplum. It had this good performance regarding all these requirements that we checked. So we went for Greenplum. Then we had this big release, the Gaia DR3, which had a really big, a new table that would be really good to start checking options for the other mission I'm working on. So I forgot to say that usually this presentation is being done by 2 people, so Pilar and myself. Pilar mostly focuses on Gaia. She has worked on Gaia for a really long time. Okay. I work mostly with Euclid, and in Euclid we still don't have public data, so we still haven't reached a data release. But Gaia, at this point, already reached the DR3. It had this big catalog of almost 2,000 million objects. So it would be the perfect way to study the following path. So how we should prepare data, how should we distribute data, how should we partition, how should we index, etc. Because these catalogs, as you can see here, there are different flavors. So we can have 51 columns to 243 columns. These are all parameters from the observations. For the scientists, this is gold. They want to see all these 1,000 parameters that I don't have here. They want to see everything. But that's not practical. So we have different flavors for the data. We have different sizes. We can compare compression. Of course, reaching these sizes, we started going to columnar tables. One of the good things about Greenplum, we can also compress data, so we can store more data on our servers, and it has really good performance. So, cool. So, I'm not going through all of this, but we started checking, just see the colors. We were studying how to prepare the databases for the queries that usually the scientists want to execute on our databases. Now you're asking me, does a scientist execute a query on your database? Do you allow that? Yes, we allow that. So we have a standard, which is called ADQL, where astronomers can write queries on that language, which includes astronomical functions, etc., to be able to query directly our data. Yeah, maybe it's not the best option, right? But yeah, that's our mission, to allow everyone to query our data. So we have to take into account the queries that they might want to do. And for that, we need to prepare how we are going to store data, formats, compressing levels, etc. So we were doing all this work in 2024. Here, there are more examples. Again, the same things. We were trying to find the sweet spot on how to execute better the queries. Also, there's extensions that we need to use. So our software, we have this layer of software that allows astronomers to write queries. So we need to have this software layer that translates ADQL into SQL. But that layer also uses some Postgres extensions, like Q3C, which is basically indexing a sphere on this, indexing a sphere. So you can make a query based on your observation. So we had to also analyze queries using these extensions. But around this time, when we were finally working with data and starting to prepare for Euclid, we had an issue. Oops. Broadcom acquired VMware, and they closed the source. So you're planning for 2018 to, 6 years. You have a mission in operations, and sorry, everything is closed. So you have a snapshot of the repository. It's an archive. You don't have commits. You don't have anything. You don't have versions. We have several versions in our several clusters, because I'm talking about one cluster, but of course we have more clusters, right? We have different versions. We have to patch those versions, and now we don't have anything. Luckily, we had the last 6.27.1, but by this time they were already on version 7, I think. But we are operating missions with software, and now we don't have how to. I mean, of course, we are software developers. If we have to learn how to patch a Greenplum, we will have to learn how to patch the code. But we have zero experience on this. So what happens now? We cannot even contact mailing lists, Slack, wherever they had for contacting people. Of course, we knew some people. In NASA, they have the Space Science Telescope Institute, which runs basically James Webb and Hubble. I don't know if you've heard of those spacecraft. But they were calling us, can you access their GitHub? We need to install some versions, and we were, no, we are just aware that nothing exists anymore. So we were able to contact some former Greenplum people. People were being fired or changing jobs because they completely changed the approach. So we have to start looking for alternatives, because we have missions in operations. We need to do something. So what can we do? We have this commercial version, Greenplum, although we were being told that the roadmap was really not clear on how Greenplum was going to continue. We were contacted by some people that were running a database called CloudberryDB. I don't know if you know CloudberryDB, anyone here? Okay. We have Citus and other MPP databases. So we started making a quick list to start having some options. So we have here Greenplum, Cloudberry, Citus, Cockroach Labs. At that same moment, they also closed the source. So also another one that we cannot use. Gigabyte, we had help Frank start looking at our extensions to start seeing if we could put our extensions in Gigabyte. So yeah, cool. We have some options. Then let's start going forward. So we start running some proof of concepts. Let's start Cloudberry. I mean, they have this bootcamp that you can download. You can execute on Docker, etc. You can create your cluster locally. Citus also more or less the same with different. I mean, one is native, another runs with an emulator. So we could see some performances there. But yeah, I mean, we need to put this in bare metal to start. I mean, Cloudberry looks promising. We have to go for this, right? No. Another problem. So due to visa, security policies, etc., we could not go with CloudberryDB. So yeah, again, we have a problem. So what can we do? Yeah, we were approached again now by DB. They were creating this product, which is Warehouse PG. It's based on Greenplum. Wow. At least we have some option, right? I mean, if we have to go to Citus, we have to rethink about everything. So let's do another evaluation. Again, Citus, EDB, same hardware, Gaia catalogs, queries. Well, scientists with data, it's like this. They start changing their focus, so now we have other different use cases to test. Cool. So again, we have different queries to run. Let's try again making checks. I don't know, maybe astronomy and photometry from engineering images from the Omega Centauri. What does this mean for you? Probably not a lot of things, but for the scientists, it's really important. Or, I don't know, here, I have a question for you. Here on this query, do you see parallax? Does anyone here know what parallax means? Okay, let's try to make an exercise for, I mean, you know, but come on, the other people don't know what's this. So if you stick your finger like this in front of you, you close one eye and you close the other one, looking at your finger, you see a jump. Your finger will jump. If you do it closer, it will jump much more. So that gives scientists one approximation of the distance to that star. So by the movement that they make, you can see if a star is closer or farther, right? You learned something today. Okay, so again, we started checking, making queries, etc. I mean, both solutions were really promising, but then we saw these two problems here. And again, we use extensions. We are still learning. We hit these bumps on the road when we were learning with the data. So these problems here are usage of open source extensions on top of our open source software that, in some cases, for some reason, on Greenplum works well for one query, on another query it works awfully, and it works better for Citus. So again, we need to work a lot, but you are running in operations, you bump into these issues, you have operating systems running, so you also need to take care of them. You cannot waste a lot of time. But yeah, we need to waste a lot of time investigating again. So we started checking value. So what's the value of one solution against the value of other solutions? So yeah, we are going to compare one commercial system against an open source system. But open source systems, we also need support. We are going to start now, and we need to rush, because do you remember the tsunami, right? So the tsunami is coming for us. We don't have a lot of time to learn how to operate a Citus cluster in order to have this mission operating again fast. So we need to make a big evaluation. We had to do a big evaluation of the value that each option could give us, because we need to swap the version that we run in operations. We cannot run into the issue that tomorrow there's a 0-day exploit. Of course, our systems are secured, but the security team will say, we have to solve this now. You cannot wait for someone to come and fix your problem when there's no one to fix our problem. Migration costs. Well, for ADBs, we just saw it. We just need to swap binaries because they are based on the same source code. So yeah, Citus, we have to ingest all the data again. I mean, we tried. Citus is really fast because it allows parallel ingestion, so it's really good. But I mean, it has a cost. Also, it has surprises. We never run with Citus. We are going to run into surprises. Support. Well, we don't have support. There used to be some support. Now, maybe a few companies can provide support for Citus, but there's no support. And now we need support. Now we really need support, because now we run into an issue that we have a lot of issues, and we need help to overcome all these problems. And also, we don't have, in the open source version, you don't have native monitoring tools or specialized backup tools. You would have to develop yourself. It's okay. I'm a software engineer. I can develop solutions, so that's okay. But my time working on missions, working on DBA, will have to be moved into developing solutions. So, of course, we have a lot of ways to overcome all the issues, but we need time. We need resources to do all of this. So our conclusions, well, I mean, Warehouse PG has good scalability, it has Postgres compatibility. They have defined a good roadmap, so they are, I mean, Greenplum 6 that we are running in operations runs with Postgres 9.4. Does anyone work with 9.4 here? Yeah, probably not. So that's our thing. We need to evolve. We need to move further. Citus also is good because we are running already on 17, so it's good. It's modern. It's good. We can use it. But the conclusion is that, I mean, we can go for professional support. It has a cost, probably vendor lock. We don't know. We don't know the future. It's still uncertain, like everything. So contracts can change, etc. Like open source software can change. It can stop being open source and not open source anymore, like it happened to us. We have learning curves, almost nothing coming from Greenplum, going to Warehouse PG, going for Citus. I mean, I said we run 100 Postgres, so we know how to run Postgres, but of course we don't know how to run Citus. It should be that hard, but I don't know. If you look into the internet, you will see that a lot of people run, but a lot of people run into issues as well. So there are fun alternatives, other alternatives. I had yesterday a good discussion with Alistair and Jan regarding software solution, sharding based on software. So instead of using what we have, we could develop a sharding mechanism that would allow to cover all our requirements. And it seems that in the industry there's a big interest in this. Of course, that it would mean for us to also contribute with our time in open source projects. I'm totally in favor of those solutions because I love open source, and I would like to contribute as much as possible to open source. But of course, this comes with a lot of things. Again, we don't have all the knowledge. We would have to maybe reinvent the wheel. Maybe someone in, I don't know where, also develops something, is not sharing with the world, but maybe someone is also working on this. So, yeah. What's going to happen next? Well, we just make studies and give everything to managers, and managers take decisions. So right now, we don't know exactly where are we going to. But yeah, this has been our journey. So I'm, again, sorry for the delay in the beginning. I had to rush a bit to catch up with the time. And if you now want to make any questions, not regarding that thing that it's flying in space, of course. I'm not going to answer to that. Remember, no comment things.
Thanks a lot for your talk. So all queries except one that I saw was just no joins, simple select on very wide tables. Did you consider the ClickHouse? It should really...
Sorry?
ClickHouse, another database engine, should work perfectly in that design. As wide tables, just all up type of load, open source. I mean...
Yeah, maybe here I don't have all the cases. I'm not seeing, yeah, here. This case, for instance. We do a lot of joins. So although it's not reflected on these queries, I don't see a lot here, especially with Gaia. But with Euclid, we are going to make a lot of joins with other catalogs. So the idea on this is that scientists also want to do cross matches between catalogs from different missions. So the idea is that you can make, I don't know, a query using a Gaia catalog and a Euclid catalog. They are different missions. So one is looking for stars in the Milky Way. The other one is studying dark energy and dark matter, is creating a 3D map of dark energy and dark matter of the universe. But scientists will want to correlate information because with Gaia, they can see the movement of the stars, and maybe that information is really important for looking into a Euclid catalog. So, yeah, I mean, we haven't checked ClickHouse, but our use case for Euclid is that we are going to have a lot of joins, which, if you have worked with distributed databases, that's a really good challenge. And one of the things that I mentioned in the conclusions that I don't have time to go through everything, it's more clear on how to distribute well for joins using Greenplum. We run into issues with Citus. So Citus allows you more sharding models and also sharding optimizations for joins, but we actually run into problems when trying those approaches.
Thank you for the talk. Could you maybe please elaborate on this cloud-buried security issue?
No. Yeah, I can say that you have to consider the origin of the software and the reputation that the software has in order to be adopted for an operating system. In this case, the origin of the software comes from a set of countries that are not that we are not allowed to run software from. Of course, that we run Postgres. Everyone can write inside Postgres, right? But at least it's governed by you guys, okay? And it will be secure. I hope I don't run into troubles by answering this question.
Hello, thanks for a very good presentation. I am a bit interested in the sharding part that you mentioned. So can you explain a bit that, do you have your data in like multiple databases, or are they really fat tables and that is why you want to do sharding? A bit more insight on
So we
that.
have really big fact tables. And they are distributed two ways. The first way to try to be that each segment, a segment is a Postgres instance, okay? Each worker node has 5 instances, and we try to have the same number of rows approximately on that table among all of the segments, okay? Then, for joins, you also take into account the algorithm that does the distribution to use foreign keys and primary keys, and the system will try to collocate tables evenly the same way in order for the joins to run. Sorry. I don't understand the question, sorry.
So you already have a shard key for all your tables, maybe synthetic or organic?
I don't get you, sorry.
The shard key for the
Yeah.
tables,
Yeah.
do you have that for all the tables?
Yeah, obviously. So most of our big tables, they have, when you create a table, you can define the distribution key. So when you create a table, you have to pass all these options to tell them you want a append-only column-oriented table, and it's going to be distributed by the source ID. So the source ID is the unique. A source is a source of light. That's a star. Might not be a star, but it's a source of light. So that's distributed by the source ID. But if you need to make joins with other tables, you can add other clauses for the sharding.
Well, I'm very sorry to cut you short here. I know there are more questions, but lunch is being served in the room here and downstairs. So sorry to interrupt you here. Here are some gifts as a speaker. Thank you for the presentation. Will you be around for more questions?
I'll be around until Saturday, so you can approach me and ask any questions you want, except for that flying thing, okay?
Well then, thanks again, and well, enjoy your lunch.
Okay, thank you.